Okay. My name is Gregor Harnick, and I decided to do my presentation on Google's PageRank algorithm. So, just a little bit of background overview. Whenever you make a search online or on the internet, whatever you type in, somehow you have to go from that to the results of everything in order of hopefully like how important it is or like how well you'll be able to use it. And so I'm talking about how the algorithm that does this works, or the algorithm that did it before like today's, but a very important stepping stone in it for Google. And so a lot of times it'd be easy to assume that this algorithm could just be okay, checking for keywords, like okay, they searched for banana pancakes. We're gonna show every single like banana thing of banana pancakes. That's like how you differentiate between food and the song by Jack Johnson. And so a way to get like a more relevant result is using what's like linked to it. So if there's a page that links to another page, we consider that page that's like linked to important. And if lots of pages link to the page, then that page becomes more important. And if a relevant page transfers to another page, then that importance transfers over. And we can assign ranks to pages using this, using matrices. And so our motivating example behind this, as shown here, just gives the example of four websites. So website 1, 2, 3, and 4. And website 1, as we can see, links to pages 2, 4, and 3. Website 2 links to pages 2 and 4. Website 3 only links to website 1. Website 4 links to websites 3 and 1. And we can use a transition matrix to do this. And a transition matrix basically just documents how a website links to other websites. So we can see website 1 does not link to website 1. So there's a 0 here. And it links to the next 3. So there's a 1/3. And as we can start to observe here, this matrix is stochastic or Markov, where every column sums to 1. And this is important for later, and we'll dive into that. And so website 2 links to 3 and 4. So we see third and fourth. Its importance is split. And website 3 links to website 1. So there's just 1 there. And 4 goes to 3 and 1. So we have 1/2 and 1/2 of those two. And the way we go from this to how important each website is, and if you're like searching something up, we can go through a dynamical systems point of view and a linear algebra point of view. And so the dynamical systems point of view is if we assume at first importance is equally distributed. So we have a vector of 0.25. So each website has importance of 0.25. So website 1, 0.25, website 2, 0.25, 3, 0.25, and 4.25. We can take our matrix A here, the transition matrix, and we can multiply it on this vector, and A to some power times our importance importance vector, will eventually just equal A to the power minus 1. So A to the K equals A to the K minus 1. So it will converge as we get to a high enough power. And so we can see here for like this example, I don't have the math shown, but we go from by multiplying this A and just keep multiplying that onto this vector and then the results, we start at 0.25 and we get to this right here, or 0.38, 0.12, 0.29, 0.19. So that shows the importance of each website. Website 1 has an importance of 0.38, website 2 has an importance of 0.12, and then 0.29 for website 3 and 0.19 for website 4. And we can see once we do that first multiplication, we're going from V and we're starting to approach this. And the reason that this always works for a system that's set up like this, we'll get into a little bit more going over some theorems, but the general gist is that A, as we talked about earlier, is a Markov matrix. Every column adds to 1 here. And so what we know about Markov matrices is the max eigenvalue is 1. And specifically the Markov matrices we use here, which I'll get into later with the theorems, is that there's only one eigenvalue of 1. And we know that this will eventually lead to the matrix to converge, is that there's only one eigenvalue with a value of 1, and the rest of the eigenvalues are less than 1. And because the spectral radius of like that eigenvalue that's 1, that eigenvalue will take over. And so that eigenvector related with that will eventually take over, where every other eigenvector and like the importance of it will eventually approach 0 because the spectral radii of those is less than 1. And so if you're multiplying, let's say 0.5 times something, it goes from the value 1 to the value 1/2 to the value 1/4. So we go 1/2 to 1/4 to 1/8 dot dot dot, and we see we approach 0. And same with, even if it's 0.99, you're still going to approach 0. Where 1 to the n just equals 1. So this this eigenvector with eigenvalue 1 takes over. So this is that eigenvector. And another way we can see that is through the linear algebra perspective, where we have the same setup and we multiply it on. And we know that like we just need to find the eigenvector of 1 for this system. And so we can go from this to the system of linear equations, where x1 is x3 plus x4, and x2 is 1/3 x1, and so on and so forth for this one and this one. And we need to find the vector here that can replace this. So some other v, where this times that vector is equal to that vector. And so if we solve the system of linear equations, we get 12, 4, 9, 6, where we can just like see that this like masks out, where x1 is x3 plus 1/2 of x4, which is 9 plus 3 equals 12, which is x1. And we see x2 is 1/3 of x1, where 12 over 3 is equal to 4. And this just continues to work. And then we know it has to stay like Markov, where the sum goes to 1. So if we just normalize it, where in this case 12 plus 4 plus 9 plus 6 is 31, and we just multiply everything by 1/31st, we get this, which happens to be that same PageRank vector for the system as the convergence method that we used above. And I think it's really cool how both of these methods work. There's also a probabilistic perspective, which is also very cool, but I'm not going to get into that today. Up above, that system was a little bit unfortunate for us. And so now we're going to go into cases where that system's a little bit less fortunate than we want. So this is when in the system, the system that's like linked together, we're going to talk about if there's nodes that are dangling or components that are disconnected. So for example, a dangling node is a node where it's like, if we have a node like 1, node 2, node 3, and we have a node 1 to 2, 2 to 3, and then we also have a case where there's 1, 2, 3. We have nodes 1 to 3 and 3 to 2, where 2 just doesn't go anywhere. And so you're stuck with this node 2, where you get there and then you just stop. That's no good. And a disconnected component is where if we have like node 1, node 2, node 3, and node 4, look like 1 to 2 and 3 to 4. And there's just no 1 to 3, 2 or 2 to 3. So once you're at 1 and 2, you're stuck at 1 and 2. You're stuck at 1 and 4. When you're stuck at 3 and 4, you're stuck at 3 and 4. So a way we can fix this to think dangling node case, because the way that works is when you're doing the multiplication up above in the, for example, the dynamical systems, you're getting a row of zeros. I mean, a column of zeros in this transition matrix. And that will just make it converge to the value 0. And obviously, that's not right. And so an easy fix for that is just to equally distribute the probability for that one. So if there were 4 nodes in the system, you just do 1/4 for each column. And if there were 5, you do 1/5. Just do 1 over n is equal to everything. And that keeps that stochastic property, because 1 over n times n is just going to be 1. And then for a disconnected component, that we have. That's a little bit trickier to fix, but it's still not really bad at all. Where you have the thing with disconnected component is you'll get two eigenvectors with the eigenvalue 1, which we can't have for this case, because then it's which one's the solution. And they're not going to be a scalar multiple of each other. It's just not going to work. And so that's where we get into the solution of Page and Brin. They use a damping factor so that the user can teleport from any node to any node. And so the damping factor that's regularly used in practice is 0.15, where each node, where you add this to the previous factor. So you get a new matrix M instead of the A we used above. M is equal to 1 minus the damping factor times A. So in this case, it would be 0.85A plus 0.15B, where B is just 1 over N times a matrix of ones. And so this keeps the every column stochastic or Markov, and it allows you to teleport. So you no longer get stuck at any nodes. And when the components are disconnected, you normally stay within your, if it's again 1, 2, 3, 4 example I showed, you're normally staying 1 and 2 when you're at 1 and 2. And sometimes you jump over to 3 and 4. But when you're at 1, you normally stay in the path. And before I get into example, a couple of theorems that help this work is the Perrin-Frobenius theorem, where if M is a positive, so every value in it is greater than 0, and a column stochastic matrix where every column adds to 1, then we have an eigenvalue. 1 is an eigenvalue in the matrix, and there's only one case of that eigenvalue. 1 is the largest eigenvalue, with all the other magnitudes having a magnitude less than 1. All the other eigenvalues having a magnitude less than 1. And this is what I was talking about above, where that's why the dynamical systems method works. And finally, is that eigenvalues corresponding to lambda of 1 have either only positive or negative entries. In particular, for the eigenvalue 1, there exists a Markov eigenvector. And this Markov eigenvector is what we're looking for. And so it just says that that exists. And the power method convergence theorem is let M be a positive column stochastic n by n matrix, and then denote V the probabilistic eigenvector corresponding to the eigenvalue 1, and let Z be the column vector of entries 1 over n. And so this is kind of just again saying about the method above, where eventually Z will converge when multiplied by enough m's, m to the power of k, will eventually converge to this probabilistic eigenvector, which is what we're looking for with the PageRank algorithm. And so it's cool that these are fully proven, proofed out, and super helpful to us. And going into a sample problem on this, I chose problem 3 out of problem 4 from the Cornell lecture notes that I used to create this presentation. And it's computing the PageRank vector of this graph, considering the damping constant P to be 0, 0.15, 0.5, or 1. And so I chose this graph because you can see we have, I guess, just a main issue here where it's this 1 is not connected to anything. There's no output from 1. And that's pretty much it. And so initially I made a vector map. So 1 goes to nothing, so it's all zeros. And then 2 goes to 3 and 5. 3 goes to 1. 4 goes to 2 and 5. 5 goes to 4 only. And then 6 goes to 3 only. And so first, to fix this, I took the liberty of changing this 1 from 0, 0, 0 to 1, 6 for each. So it's that first solution when we have a dangling node. And then I just started mathing it out. So I used the solution of Page and Brin to apply damping factors here. And so I set it to everything. So these are the equations for the damping factor of 0, 1, and 5, a half and of 1, where you're just doing the math and multiplying it out. And then I computed the m's. So obviously if the damping factor is 0, you're just getting m is equal to a. So I just left it how it was. And then if the damping factor is 0.15, you get 0.85A plus 0.15B. And again, we can see this keeps it. So this row stays because everything's already equally distributed. And then for the next row, we can see we go from 0, 0, 1 half, 0, 1 half, 0 to 0.025, 0.025, 0.025, 0.025. Now then we go from 1 half to 0.45, where this is still stochastic. This sum of this equals 1. And then the next row, I decided to only compute the values that were non-0.025. So that's what the blank space is here. We get 0.875 for the values that were 1, 0.45 for the values that were 1 half. And after that, we have our value of 0.5 for our damping factor. And so again, this row stays 0.1667. And then we have 0.083 for all the empty things. And then 0.33 for the values that were 1 half and 0.583 for the values that were 1. And then if our damping factor is 1, where we're totally just removing this A, so this doesn't even matter anymore, then B, every entry is just going to be 1/6 here because there's 6 vectors. So 1/6, it's going to go all the way here, all the way here, and all the way there. And then I made some code to compute the page ranks. So first I'm just going to briefly go over the code because I thought it was like super easy to code. I use ChatGPT to code this, but it's just want to like walk through kind of how it works. So first I just compute PageRank, and it takes in a vector A, initial vector B, and then the value of our damping factor, P, and then just how small we want the change to be when we say, okay, it's done converging. And so we taken all these, and we just do the formula. And the formula happens. And then right here, we just iterate. So for in range max iterations, which we did 100, we just go new vector, we just do the multiplication, and then we normalize it. I tried taking this line of code out and in, and it did not matter here. So you actually don't need it. And then I said, if the change is less than the tolerance, you get the new vector. And if you go all 100 iterations and it's still changing, then you just return the new vector anyways. And so going through the PageRank algorithm, we got our damping value of 0. We got the importance of vector 1 here, which again is this. I'm just going to move this down to here so we can see the problem again. Is we have the importance of 1 is 0.162 or 16%. The importance of 2 is similar. And the importance of 3 is slightly less. The importance of 4 was 0.27. The importance of 5 was 0.24. The importance of 6 was 2%. And these results, honestly, were not what I expected, where the importance of 4 being as high as it is really surprised me. And same with the importance of 5 makes a little bit more sense because there's 2 nodes coming into it. And I think maybe that the importance of 4 is so high because 5 is more highly weighted. But that was super interesting to me. And we can see, like, as we go from no damping factor to the damping factor of 1, where that 1/6 matrix just takes over, where every importance is just equally 1/6, because our solution is 100% damped out. And we can see as we go from the damping factor of 0 to 0.15, 2.5, these values approach our total of 1/6 for everything. So we go from that to, for a damping factor of 0.15, we get 18%, 15%, 16%, 23%, 21%, and 5%, where everything is approaching this 1/6 value. And then, which is like 0.166666 and 7 at the end of it to just kind of even it out. And we can see when we go from here, we get a little bit closer to everything being at that. We get a little bit closer again. And when we go to the damping factor of 0.5, we get 19%, 14%, 18%, 19%, 18%, and then 10%, And so this really small value doubled, and then it doubled again here. And everything else, I thought it was really interesting how like this one increased here, but then it's decreasing down to 1/6 at the end. And I found that super interesting, where it's even like the average becoming less extreme. This one became like a little bit more extreme, or this one became like a lot less extreme away from that value. And yeah, that's just a brief overview of Google's PageRank algorithm. I think it's really cool how it works, and honestly, surprisingly simple. How they're able to make a problem that could be so complicated, where it's how do you choose which website is the most important, is the most relevant, and you can break it down to a pretty fundamental linear algebra problem where all you have to do is take a matrix to the nth degree and then multiply it onto something, a vector, or make a system of linear equations. And obviously, they're not doing this for all of the millions and millions of websites on the internet. But if you have a website, all the links coming to it are normally not going to be a crazy high number. Where it's you can get a system that's not super massive in size, and two, that tends to be pretty sparse because even if you have a couple websites that have a lot of websites linking to them, most of the websites in the kind of like the network that you choose, that they select for doing a PageRank thing, are not going to be linked to by many other websites. The matrix will have a lot of zero values. That's another thing that just makes computation easier because, kind of as we saw in my calculations, finding those M vectors, those M matrices, there's a lot of zero values, all this empty space, zeros. And there's also a lot of, not zero values, but the same value here to there. And that's with the damping factor. But in the original matrix, or A, there were a lot of zero values. Where we originally started with this, where there's only 1, 2, 3, 4, 5, 6, 7 non-zeros out of the 36 values in the matrix. And then this is a very easy thing to do. And then going from that to this is a very simple equation. And that is super interesting how we're able to do something that seems so hard to do, and that would be impossibly tedious manually, and how we can set up an algorithm and use linear algebra to solve this very eloquently and surprisingly simply. And it's a very small amount of lines of code. And I'm surprised. I'm sure that they use more complex and like more refined methods to do it in real life now today. But even the fact that I can run something this small super easily is mind blowing to me. And yeah, that's been my presentation on the PageRank algorithm and just a brief overview of it. Thank you.